Good day to everyone. I am Darius Andriukaitis, co-chair of the conference. You probably got emails from personally me. And unfortunately, today the chairman of the session was unable to take part in due to unforeseen reasons. So I will substitute him, and today we have the first session named Electronics, and we have 5 presentations in total. The first presenter, Worawut Kulapong, okay, is ready, so the floor is yours.
Okay, thank you very much.
Just I forgot to mention that we have around 18 minutes for presentation and discussion, so please keep in mind.
Okay,
please.
I got it. Okay, thank you very much. Good morning. Sorry, the getting from the Thailand is good afternoon is already. My name is Worawut Kulapong, and I introduce my co-author member is Winai, Jaikla, Surapong, Siripongdee, Sotner, Peerawut, Suwanjan, and Amornchai, Chaichana. Today, I would like to present a research article entitled "The Design of the Series Negative Resistance and the Negative Capacitance Simulator Use Single Commercial IC LT1228 Base for the Application to the Sinusoidal Oscillator." Okay, my presentation is divided to the 5 parts. First, I will talk about the introductions. Then I will discuss the circuit description. Third, I will show you about the simulation results. Fourth, I will show you about the experiment results. And finally, I will talk about the conclusion. It should only take the 18 minutes for your time. I would be glad to answer your question in the end of presentation. Let's start to the first part about the introduction. The sinusoidal oscillator are the crucial analog circuit in numerous the electrical and the engineering application, including the telecommunication sound system, measurement system, instrumentation system, and the control system. The design of the resistance, the inductance, and the capacitance simulator for the use instead of the passive components has been the continually proposed. The simulator are often constructed from the active and the passive parts, including the resistor and the capacitor. But however, the inductor is not preferred due to the size and the expenses. Okay, next for the simulator of the resistor and the capacitors can be created in the both passive and negative form. The negative resistor and the capacitor simulator are utilized in the varieties of the application. But in order to develop high performance circuit with a few passive and the active components, the active building block of the we call ABBs have become to the important factor in the design of the contemporary analog signal processing system. But in my paper, is the LT1228 is becoming with the operational transconductance amplifier and the electrically variable transconductance gain, so we call the GM. Its made circuit can operate and control with the microcontroller or the microcomputer. But the objective of this paper proposed to the alternatives method for the synthesizing the sinusoidal oscillator using the series of the negative resistance and capacitance simulators. The connect to the parallel with the grounded resistor and the capacitor, and the control impedance by the electronic coil and the amplify output gain without the require any the external amplifier circuits. Now I have the finished explaining about the introduction. Let's take a look for the second part about the circuit description. By the figure 1, sinusoidal oscillator based on the series negative resistance and capacitance connected in parallel with the resistor R2 and capacitor C2. The synthesization of the sinusoidal oscillator based on the negative resistor and capacitor, there have been several alternative approach proposed at the potential ways to synthesis to the sine wave oscillator. But in this paper, the synthesis make use for the arrangement of the series negative resistance and capacitance that called the Rn and the Cn. They connected in parallel with the resistor and the capacitor as shown in the picture. That the figure, as I told earlier, that's one we can obtain the characteristic equipment by the equation number 1, and as well as the frequency of oscillator. We call the shorten in the FO. We can obtain by the equation number 2, and the last one we obtain the condition of oscillation. We call the CO in the equation number 3. But if you see clear in the number 2 and number 3 is clearly very clearly that the FO and FC, the FO and CO is not independently controlled. But however, if the parameter in the negative resistor and capacitor value is matching in the same value, FO and FC could be the control independently. Let me show for the next one. Overview of the active element LT1228 as I proposed in this paper. This active device consists of the transconductance amplifier that we call the OTA. And then next one is consists of the current feedback amplifier that we call the CFA. The electrical relation between the input and output terminal of the LT1228 that's shown in the metric like as equation number 4. And as shown in the figure number 2b, the transconductance adjustable by the DC bias currents that we call the IB at the pin 5. That relation between the GM and IB and thermal voltage can be derived by the using equation number 5. For the next one, the proposed grounded series negative resistance and capacitance simulator use the LT1228 and the contacted use the single resistor and the single grounded capacitor. The input impedance of the proposed circuits can be obtained by the equation number 6. Is capable of the electrical control through the IB, because this term is with the DM depends on the IB. As I described in the last presentation, the value of the equipment, the value of the equivalent, the negative capacitance and the resistor that's described in the equation number 7 and number 8, that's significant advantage of the design, because that value can be electronically adjusted by the external bias current as IB. Next to the series negative resistance capacitance based sinusoidal oscillator circuits with the amplitude controllability. These circuits they call the short name in the sinusoidal oscillator. The sinusoidal oscillator in the figure number 4A use concept from the RC parallel oscillator circuit in the figure 1, but construction used from the grounded series negative resistance and capacitance simulator from the figure number 3A. Instead of the negative RC and connecting the grounded resistor R2 and the capacitor C2 to the input impedance node in parallel. Okay, from circuit above, we can obtain the characteristic equipment by the equipment number 9, and as well the frequency of oscillator FO by the equation number 10, and the last one condition of oscillation by the equipment equation the number 11. But from the characteristic equation by the number 9 as above, if we determine the C1 equal to C2, the FO and the CO that can obtain the new equation by the equation 12 and the equation 13. But utilize the equation number 12 and the 13, the FO can be controlled separate from the CO by the utilizing the C1 and C2 by this one. And additional in this, the equation number 13 that you see that can consist of the GM can set the condition of oscillator in the manner that may be the control independent from the FO as well. That's all I want to say about the circuit, the description. Let's turn to the third part with the simulation results. The condition of the simulation result as I use the SPICE simulation software that circuits the based on the figure 3A that in my presentation, the base for the circuit, but and the power supply is supplied by the voltage set, the plus and minus 5 volt. The bias current IB was set to the 206 microamp. To the upturn, the minus 2.06 nanofarad from the equivalent negative capacitance in the equation number 7, and the upturn the minus the 485.67 ohm from the equivalent negative resistance in the equation 8 need to set the C1 to the 1 nanofarad and the R2 the 1 kilo ohm. Okay, let's take a look at the low frequency of the figure 5. You can see the magnitude of the impedance is in the red line, and the phase is the blue line. And the theoretical of from the calculation equation is a backdash line. The simulation result behave like equation number 6 as shown in the picture, but when we look closely in the graph as the nearly the 1 megahertz until the 10 megahertz, the simulation result phase is slightly different from the theoretical value because the effect from the parasitic resistance and the parasitic capacitance of the active components, as we showed later. Okay, go to the figure number 6. According to the equation number 5 and number 6, the magnitude of response can perform electronically tuned by the chain the IB, and then the chain GM as well. The figure 6 show magnitude when I change the IB to the 51 microamp, and then change to the 103 microamp, and finally I change the 206 microamp. That magnitude can change by tune by ID. This proves already. And next one, the last of the I propose the simulation of the sinusoidal oscillator. I use that simulation based on the circuit in figure 4. The voltage set to the plus and minus 5 as well, and the capacitor C1 and C2 is set in the same value, is 1 nanofarad, and the R1 and R2 set to the 1 kilo ohm as well. From that value, refer by the equation number 12, this circuit will obtain the frequency of oscillator about the 159.15 kilohertz. And then the waveform of the oscillator. But this oscillator, when I measuring from the SPICE that show frequency about the 159 is the different from the theoretical a bit, not too much. And then the picture show the spectrum of oscillation frequency, as well as the total harmonics about the 0.5 % THD. And next one, according to the equation 12, the frequency of oscillator can perform electronically tunable by the chain the C1 and C2 together, by the set the boards of the capacitor in the same value. For the response graph, in the last one, it showed when we set the C1 and C2 to the 1 nanofarad, and the frequency of oscillator is about the 159 kilohertz. And the green one that show when the C1 and C2 set to the 0.8 nanofarad, and we obtain the frequency of oscillator about the 199 kilohertz. And last one, the blue dashed line, we set the capacitor C1 and C2 to 0.6 nanofarad, and we obtain the frequency of oscillator about the 264. Does it mean that we can the change frequency of oscillator by the change the C1 and C2 as proved by the equation 12? Okay, go to the next one. According to the equation number 15, the output VO2 gain is depends on the number of the resistor R3, that the gap proven by the change R3 invariance in the variety value. For the example, the VO1, instead of that stand for the yellow line, the original of the Vout, and the blue dash line instead for the Vout, which gain when we set R3 to the 10 kilo ohm. Okay, I have finished explaining for the simulation results. Now we will turn to the fourth part with the experiment results. The experiment results with proposed sinusoidal circuit oscillator with the grounded series, the negative resistor and the negative capacitor simulator. We configuration the circuit by the set the C1 and C2 to the 1 nanofarad. And we set the R1 and R2 in the circuit to the 1 kilo ohm. For the value by the equation, we will got the theoretical value for the frequency of oscillator about the 159.15 kilohertz. That the figure that illustrated for the experiment configuration in detail built by the baseboard. Okay, go to the oscilloscope results. In the figure, the 12A that demonstrate that frequency of oscillator in the proposed circuit. I made sure that frequency that obtains about the 171.8 kilohertz at the node VO1, with the 0.6% percentage TFD. This frequency is close to theoretical value, but it's error about the 7%. And the next one's the figure, the 13, at the Vout2, which gain that depends on the R3 that I was set the value to the 10K in order to the obtain gain about the 8 times of the at the node V2. The frequency that we got about the 171.6 kilohertz, and spectrum at the node Vout2 is about the 0.81% TFD. Okay, I have finished explaining about the experiment results. Now we turn to the last part with conclusion. This paper presents about the new methods of the synthesizing the second order sinusoidal oscillator based on the series negative resistance and capacitance circuit. The new series negative RC simulator as also has been proposed at the the forming of the sinusoidal oscillator. The proposed simulator electronically controllable, the realized by the single LT122S by the R1 and the C1. The sinusoidal oscillator construct from the connect to the R1 and C2, the R2 and C2 in the parallel. Then the next one, the frequency of oscillation can be the adjust simultaneously change to the C1 and C2 without affect the condition of oscillation. And the connecting the R1 between the X and the bill, they can adjust the gain as well. And the last one, however, the parasitic element present in the LT1228 can affect the circuit performance as demonstrated in the simulation and experiment. I have already discussed about the conclusion at the end of my presentation. Thank you very much.
Okay. Thank you. Thank you for the presentation. Do we have any questions? Oh, probably no. I can't see any raised hands. Okay, so I have one question about the difference between simulation and experimental results. How do you think, who made the influence, the significant influence to the measured results? Because the simulated and experimental results slightly differs.
Yep. In my opinion, that's one, the simulation is just only the characteristic from the model of the macro model from the SPI model, but in the experiment results, as we show in the picture first, is that a loss of the error. That the first one that come from the parasistics of the LT1228 itself, and another one is from the we cannot use the exact value what the design for all the intent to use in the circuit. For the example, for the R1 and R2, I have to set to exactly 1 kilo ohm to the same as the simulation, but in actually is the value the resistor and the capacitor is have error by itself. That it doesn't mean when you use that equipment components, passive component construct in the breadboard is will the total of the error is in the finally is total is the error is too much more than for the simulation only in the computer. That's why in the experiment result that different too much from the theoretical and the simulation. That's my opinion.
Okay. So thank you for the answer and thank you for the presentation.
Okay, thank you very much. Thank you very much. I stop the share.
Yeah, yes. And I would like to invite Abhash Kumar to make the second presentation.
Yes, sir. So let me share my screen. So general introduction. So we all know there is an ever increasing demand of AI in the recent area. So which is often surpassing the human activity, this AI based systems and algorithm. We can see here in the flow chart, there is huge demand of AI in different areas like IoT, robotics, healthcare, gaming, social media, and so on. And the demand is ever increasing in all the different fields. So inspired by such positive outcomes, the people are working on different AI-based means neuromorphic devices. So so what is the neuromorphic computing? So neuromorphic computing is nothing but it's a brain-inspired learning algorithm which people are trying to run on the hardware. So why hardware? Because often a hardware-based system is preferred because it can be operated at isolated places, and also it is observed that the hardware-based algorithms are more faster than the software-based implementations. So people are working on this neuromorphic computing thing to get our thing intelligently done on the hardware itself. But again, in the recent what the problem is the von Neumann architecture. The people are implementing this algorithm on the von Neumann architecture, which increases the latency and energy cost. So because there are different memory and computing locations on the chip, so due to transportation between those two localities on the chip, a huge amount of bandwidth requirement as well as energy requirement are needed. So to avoid that, what people are doing is to compute at the same place in the memory itself to avoid those problems. So here it's written, it's a neuromorphic computing response to this problem by taking the inspiration from the main, as I have already discussed. So first let's come to know what's a deep DNN, deep neural network. As it's a well-known architecture, so in deep neural network, nothing but what it does is it's carry out weighted summation of inputs and passes through an activation function. Here sigma we have denoted and generates the output. So this is the whole functionality of deep neural network. People try to implement such network on the hardware chip, and the advantage of this network is it's a very versatile. It can be used to perform any sort of prediction or any sort of classification work. So here are the brief overview of the previous work. So actually the problem with the previous neuromorphic hardware is that it consumes a large amount of energy. It is observed that the human nerve cell consumes around some few femtojoules of energy just per spike. But for most of the previously proposed architecture, the energy consumption is quite high. And this is for a single spike. But as we all know, for training as well as for inference, a large number of, even for big data set, few thousands or few lakhs of spikes would be generated to train the network. So in such cases, the energy consumption would be so high that it might burn the chip itself. So here also the problem with is the energy. Here is it's in milliwatt, or here it's in picojoule, which is still high compared to human nerve cell. So coming to our proposed work. So this is the proposed neuromorphic device. Actually, in all the connections are modified at the synapse of our human nerve cell. There it's shown it's a synapse. It's a connection of two nerve cells, and the strength of the connection is defined by the weight of those connections, which is modeled as W in our neural network. So in our proposed device, so as you can see in this new synapse of human nerve synapse, there is an input signal, and it generates some output depending on the synaptic weight, and then propagation is performed to update those weights. So to simulate such a synaptic activity on electronic devices, what we have proposed is ours is a charge trapping transistor having drain which is acting as the input, and the source current is acting as the output, and these weights are modified by charge trapping inside this charge trapping layer. So first have a look at the details of our proposed device. So we have employed the traditional silicon based devices having SiO2 as gate this oxide, and this dopingless channel, and having a doping of 10 as 18 per centimeter cube, and one nitride device which is used for the charge trapping. So we have employed Silvaco TCAD to simulate our device, where we have incorporated these models. There are different models used in Silvaco TCAD to simulate different sorts of devices depending on their functionality. So our which have Connes rich model, which is recommended for silicon. CBT is used to model parallel and perpendicular fields inside the device. And similarly, FLD mode for silicon, and again, these are all the recommended models in the Silvaco TCAD documentation they give. And PF.nitride is used to model the charge trapping in within the nitride layer. And quantum tunneling is used to carry out that tunneling from the bulk electrode to nitride. How this is performing, we will see in the upcoming slides. So this is our proposed device working. So actually, what we are doing on applying sufficiently high voltage on the bulk electrode, we can carry out the trapping inside the this nitride layer. This dotted line is showing the nitride layer, and there, as you can see, there is a small 2 nanometer width oxide layer, through which we can carry out the tunneling within the nitride layer. And actually, this charged the trapped electron within the nitride layer will obviously they will modulate the conductivity of the channel, and hence they will modulate the output current. We all know very well, because any electron charged trapped electron on nitride layer will push away the electron formation, means channel formation in the doping this channel layer, and will means modulate the output current. So depending on that, we can carry out the modulation of weight, because through nitride layer we are denoting the weight. By trapping different amount of charges in nitride layer, we can modulate the weight. This is the proposed device. So looking to our simulation results, so this is the working of the device. Actually, this is the gate layer, this is the channel, this is the in between oxide layer through which the tunneling will be done. This layer is denoting the nitride layer. We have given the index as well, and this is the bulk output terminal. So when we apply sufficiently positive voltage, which electron will be trapped in this nitride layer, and on applying sufficiently negative voltage, the electron will be detrapped from this nitride layer. As we these are the simulated result which is shown in this figure. So from simulated results, these are tracker from Silvaco TCAT, it's a Silvaco TCAT result. We can see that initially there were almost no trapped electron in this nitride layer, but on subsequently applying the positive voltage on the bulk electrode, the sufficiently high electron gets trapped in the layer, and again on applying negative voltage on the trap layer, as in the second case, we can see the electron gets again detrapped. So this way we can verify that okay, our device is working. Next is the IV characteristic of the device. So any device from our device, what we are actually doing, we are trapping the electron on the nitride layer to modulate the conductivity. In the other words, we can say we are modulating the threshold voltage of the device. So we can clearly see that on applying VV right, which is nothing but the positive voltage, and we are denoting VV right as charge trapping inside the nitride layer. So a depression is seen in the IV characteristic. Thus we can conclude that the threshold voltage has changed. And again on applying the negative V raise voltage, it is we are means indicating that we are removing the electron from the nitride layer. So it's showing the facilitation behavior. So again changing the threshold voltage of the device. So this way we can carry out the learning within the device. So learning is the most important for any neuromorphic application. The device should be able to learn but how it learns actually it by tuning its parameters. So one of the widely used parameter to tune is threshold voltage. That is the channel conductivity, which is mostly used in the neuromorphic device design. So next is the transient simulation. On applying subsequent, again you can see the VB is this bulk voltage. On applying subsequent positive voltage, this charge trapping can be observed in this nitride layer. These negative charges continuously increase, due to which the IDS current reduces, and it simulates the learning behavior of the device. Again, on applying sufficiently low, here we have chosen to be around 6 volt as positive, means right VV right volt pulse. This is VV right, and VV raise pulse to be around minus 8 volt. So on applying, again this conductivity changes. Coming to our main motive of this whole work was to reduce the energy consumption compared to previous work. As we have observed that the energy consumption was observed to be 0.1 femtojoule per training pulse. The maximum Emax was observed calculated to be around, and EME was calculated to be around 0.05 femtojoule per training pulse, which is the lowest, which is to the best of our knowledge. So this way we were able to reduce the energy consumption to human actually nerve cell range. The human nerve cell range is also in few femtojoules also the energy consumption is. So now this is the comparison with the previous work. As you can see, the for our proposed work, the energy consumption was observed to be the lowest. Yes, it was observed to be the lowest from here. So next, so we have next what we have taken it to the next level. We have designed the circuit using our proposed device on Python, means crossing like architecture, which is a well known to simulate the crossbar neuromorphic architecture. So on this architecture, the main challenge was to implement the negative weight. As we know in artificial neural network, these weights can be both positive as well as negative, but the conductivity of most of the devices is only positive. So, but to emulate such negative weights, what we have done, we have used both the negative and positive input voltages. So what we have achieved is that suppose if this Wij means the weights corresponding to positive input, if it increases more compared to the Wij minus, which is correspond to the weights corresponding to negative input, then we can emulate the negative weight. So this was the we have designed to incorporate the negative weight as well, as we have this row means denotes the positive weight and this row denotes the negative weights by applying negative input, and these two are the biases which are provided often in the artificial neural network. So next we simulated to classify digital and logic by using this architecture. So we have used the simple architecture of three inputs to classify the means digital and gate logic. What we have observed in the fourth epoch, we were able to classify it because the very basic work of artificial neural network is classification. It creates the decision boundaries along the given data set. So here it's clearly it has successfully classified the given data set. So we have simulated its means classification capability as well on real-time data set. So so these were the some of the references that we have used in the PPT, and these are taken directly from the paper, these references. So that's all from my side.
Okay.
So thank you.
Okay, thank you. Thank you for the presentation. Do we have any questions? Okay, so
Yes.
I will ask two questions, okay? May you,
Yes, sir.
what about the experimental validation? Have you designed and made experimentally and compared results to simulated ones?
No, sir. Actually, in our lab, there were no fabrication facilities, so it was not possible to carry out means fabricate in and experimentally verify it. So we have always simulated on TCAD.
Okay, I see. And could you please open 14th slide?
14th. Okay. Okay. Yes, sir.
Okay. Where is the saturation you haven't identified in the figures?
So
uh-huh.
So this is the log means log plot. So the exponential region is shown in the linear. This is the sub-threshold conduction region, and this is the yes, sir.
But at the top should be somewhere saturation, since there is the output characteristic.
No, sir, it's not the saturation. Actually,
No?
we know that there is a V square type of dependence, means VGS minus VTH whole square dependence. So whenever we plot in the log plot, this area subthreshold region is indicated by, means this plot automatically gives the linear plot in subthreshold region, and this slightly, it's not the saturation, but it's a slightly less slope area after when it enters the square region.
I see. I see. Okay, so thank you for the presentation. And
thank you, sir.
I would like to invite the first presenter, Muhammad Peerawut, if I pronounce well, with the presentation of lossless positive negative grounded capacitance multipliers using VAC-II.
Thank you. Is my PPT visible?
Yes.
Okay. Okay. So good afternoon, and thank you for allowing me to present this paper. So this in our study we have designed novel lossless positive and negative grounded capacitance multiplier using VC2, that is second generation voltage conveyor. So I'll cover these parts. The first one will be why we are using active emulators, what is the need of them, then about the active device that I have used, that is second generation voltage conveyor, then its VI voltage current grounded capacitance multipliers, and followed by the simulation analysis results and conclusion. So why capacitor emulators? Basically, the passive capacitors, it occupies a large silicon area when we are going to fabricate it on chip. So there are many times where we require large capacitance values. So in order to uh, generate those values, what we do, we use some analog active blocks like operational amplifiers or current conveyors and use them with some small value capacitors and resistors to multiply the value of the passive capacitors and make the value higher. So these are called active capacitor simulators or emulators. So the what is the advantage? The advantage is the package once the passive capacitors are made, their value cannot be altered. But for active, we can alter the value of the capacitors on chip as well, either by making the resistors tunable or tuned. So using these two, we can make them tunable. So the value of the capacitors can be adjusted as per the need, even after fabrication. Then there are many capacitive multipliers that are already available in the literature. So there are many active blocks like dual X second generation current conveyor, current feedback operational amplifiers, or second generation current control, current conveyor. These are already used for the design, but still there are new. The voltage conveyor is relatively a new block that has been explored for various analog applications. So one of the important application is the capacitor multiplier synthesis, where they are used. So they are used in almost every field, because in phase lock loop, in frequency filters, in filtering, then in biomedical signal processing, in sensor data acquisition systems, everywhere the capacitors are required. Now, the second generation voltage conveyor is a counterpart of second generation current conveyor, where the information is processed in the form of current. But in VCC2, what we do, it is best suited for applications where the output is in the form of voltage, right? So this is basically made up of two types, the two stages. The first stage is a current follower stage followed by a voltage follower stage. Yes. So there are current followers and voltage followers. So the Y terminal is a low impedance current input terminal. The X terminal is high impedance terminal. It's basically a three-terminal device. And the Z terminal is the low impedance voltage output terminal. So here we can see that the Y terminal is the current input terminal. So it's low impedance. And the X terminal is high impedance current output as well as voltage input terminal. So whatever voltage we apply at X terminal, that is impedance is also low. So VCC can be of two types, plus, negative, or positive. Negative means when the relation between the input current and the output current, when the input the current at the IX terminal is 180 degree out of phase with the input current, then the VC2 is called negative type. So in our study, we have used both. So the first, it shows the CMOS implementation of VC2 plus, and the second one shows the VC2 implementation of negative type. So in the first, we have used the OTA type architecture for the design. The first stage is the current follower stage, Y2X, and the second stage is the voltage follower stage, X to Z. In the second, what we have done, we have used additional current mirrors to reverse the current from Y to X, so that we can introduce a 180 degree phase shift. The rest X to buffer. Then about our main topic. So we have three positive grounded capacitors multipliers we have designed, and one negative grounded capacitor multiplier we have designed. So these designs, there are 4 different designs, 3 positive, 1 negative. All the designs use a single capacitor and 2 resistors, R1 and R2. So as you can see here, so the first one, that is again grounded capacitor multiplier one, is a negative type capacitor emulator. The rest, GMC2, GMC3, and GMC4, all give the positive capacitance. So the value of the capacitance that is synthesized can be calculated from here. So the equivalent capacitance is equal to the R1 and R2. So by setting the ratio of R1 and R2 value of capacitor. C1 is the small passive capacitor that we will be using, and by selecting R1 and R2 properly, we can multiply this capacitor with a gain factor, so we can get a higher capacitor value. So the first one is negative, rest all three are positive. Now we have tested and verified these capacitance simulators on Cadence Virtuoso using 0.18 micrometer technology from Silterra, Malaysia. And we have used the voltage supply voltage of plus minus 0.9 volt. The width and length of the NMOS and transistors are taken as 3.5 micrometer and 40.5 micrometer. And the bias current we have set at 25 microampere. So this table shows the the performance parameters of the designed VC2. So this is the Y node capacitance, the X node, and Z node. So all the current gain and the voltage transfer gain is also given. So it has a DC appreciable DC range of around plus minus 400 millivolt. The DC current range ranges from plus minus 45 microampere. It can be increased by increasing the bias current, but we have kept bias current at around 25 microampere to reduce the power consumption. Next, so we have analyzed our first grounded capacitor multiplier, that is the negative one. So we have designed it for a gain factor of 5.2 by selecting R1 as 26 kilo ohm, R2 is 5 kilo ohm, and C1 is 50 picofarad. So the realized capacitance we got is 260 picofarad. So here we have plotted the ideal and the simulated responses together. So this is the first graph shows the magnitude response. The second graph shows the phase response. In the second one, we have done the time domain analysis. So in time domain, I have given a sinusoidal signal of 100 millivolt peak to peak is applied and the resulting output current is measured. So this shows because there should be a phase difference of 90 degrees. So we have verified it using the time domain or transient analysis. And also we have plotted the XY plot or the Lissajous pattern. So it verified that the phase is around near about 90 degree between the voltage and the current. Then we have done the Monte Carlo analysis so that we need to understand how the circuit behaves in when there is some process variation. So we have done it for 200 runs and we have used the Monte Carlo model provided by the foundry, that is Silterra, Malaysia, for this analysis. So as you can see here, for 200 runs, there is no much variation of the capacitance, design capacitance with the process. So the circuit is almost stable during the operation. Then we have taken the second capacitance multiplier, that is GCM2, that is a positive capacitance multiplier. We have designed it for a gain factor of 4. And we have taken R1 and R2 as 20 kilo ohm and 5 kilo ohm, and C1 same as 50 pico, and the realized capacitance is 200 picofarad. So again, on the left side, you can see the magnitude response. And on the right side, we have plotted the magnitude response with variation from temperature. So the temperature, how is it is varying with the change in temperature. So again, you see that we can, infer from the graph that the temperature variation in temperature does not affect the emulator much. Then in the same way, we have analyzed GCM3, but for GCM3, we have designed it for a gain factor of 50. So we have taken R1 as 1K, R2 as 49 kilo ohm, and C1 as 50. And the gain factor here is 50. So means it is realizing 50 times the capacity. Here we can see there is, some error introduced in the simulated result compared to the ideal one. So this error is mainly because of two things: the frequency dependent gains, the non-ideal gains that depends on the frequency, and secondly the parasitics of the design VC2. So if we can minimize the parasitics further, this error can be further minimized. Then after designing, where should we these active capacitor multipliers must be tested for some practical applications. So we have taken one simple low pass filter here R1, C1, R2, and C2. This is a simple passive low pass filter. In this, what we have done, we have replaced the C1 with our active capacitor emulator. So in place of C1, we are using our active capacitor multiplier, the GCM2 and GCM3. So we have realized it for different values, and we have plotted the ideal and the simulated result. The ideal result is all the four components having passive, all four are passive, and the simulated result will be C1. As in place of C1, we have used our designed GCM. So as you can see, the simulated and ideal results are in very close agreement. So we can say that whatever capacitance emulator that we have designed, they can be practically used for filter implementation and even for different applications. The second one, again, the GCM3 is used here. So we have used GCM3 for a gain factor of 11. And we have again replaced C1 with GCM3. And this is the response of the simulation and ideal. So here again, it follows perfectly with the expected ideal results. Now, since there was some time constraint, so we could not do the full chip level, and the facilities were also not available. We couldn't do the chip level implementation of our concept. So what we did, just for a proof of concept, we have taken the AD844 IC micro model, and we have implemented our GCM1, the first negative capacitor multiplier, on PSpice. So we have taken the micro model from the website of Analog Devices, which manufactures AD844, and we implemented that, and just to verify that our circuit works perfectly. So as you can see here also, the capacitor we have taken C1 as 1 nanofarad, R1 and R2 is taken to be 25 and 5. So we have designed it for a gain factor of 5. So the design capacitor will be 5 nano. The equivalent design capacitance will be 5 nanofarad. This is some comparison with the literature. So a number of different blocks are used for the capacitance multiplier. So as you can see, since VC2 is very recently being explored, so very few designs of capacitance multiplier are there. So we have tried to, develop some new circuits that can be added to this catalog of this application of this second generation voltage conveyor. So in this first, we have given 4 different new topologies of capacitor multiplier using VC2. The second, all the developed topology, they don't require any component matching. In many previously available devices, what the problem is, they require capacitive matching or resistive matching to work as a capacitance multiplier, and that becomes very difficult, especially in the submicron technology, to have same equal value resistances. So our circuit is free from that. Then the multiplication factor can be easily set by setting the ratio of the resistors. Then they are basically designed and they are used in low pass filtering, and we can see from the result that they perform well. So these are few references that we have used in the comparison table and in the introductory part. Thank you.
Okay, thank you. Do we have any questions from the participants? Please, no. So I would like to ask you the question about the temperatures. You estimated the performance at 25, 50, 75, and 100 degrees. What was the reason to set the 100 degrees?
Basically, the reason of doing the temperature analysis is to see that what effect does it have and the temperature has on the performance of VC2, because if the performance changes, the multiplication ratio will definitely vary. But I just wanted to show, because there are many other devices like operational transconductance amplifier. So their transconductance varies with temperature a lot. But in our device, that is not happening. So I just wanted to verify that, how it is working. So I took till 100 degree centigrade.
Okay, but does it make a significant change, let's say at 100 degrees? Or it was possible to foresee from the simulation from 25 to 75 degrees, the trend? Or
Again, sir?
Are the changes are so significant that it was impossible to estimate, let's say, from the evaluation up to 75 degrees?
No, till there we couldn't, that changes were not very significant. It was well within the range. It was not significant, but just out of curiosity, we wanted to test what happens at that temperature. That is why we have taken it.
Okay, so what about your curiosity, let's say, to simulate, let's say, up to 150 degrees or 200?
I think 100, if it works within that, the temperature cannot go beyond that for majority of our application. Even it doesn't go beyond 100 is also too much.
Okay, okay. Okay, thank you for the presentation.
Thank you.
And I would like to invite the fourth presenter, Ahmed Murat Erturan.
Hello, and welcome to our presentation. Today, we are delighted to present our work titled Detection of 2,4-dinitrotoluene by Metal-Graphene Hybrid Plasmonic Nanoantennas with a golden ratio rectangular resonator. The content of the presentation is as follows. Firstly, in the introduction section, I will discuss the definition and importance of DNT. Secondly, I will talk about the metal-graphene plasmonic nanoantennas that we use to detect DNT. I will explain the advantage we achieved by utilizing this hybrid structure. In the third step, I will elaborate on the golden ratio rectangular resonator used in the plasmonic structure. Lastly, I will discuss the results we obtained. 2,4-dinitrotoluene, shortly DNT, is a crucial precursor in the production of TNT, an explosive compound that falls under the category of nitroaromatic compounds. It's a commonly used yellow crystalline solid in the production of explosives, dyes, and pesticides. Due to its toxic and potentially explosive nature, DNT is considered a hazardous substance. What are hazards of DNT? Firstly, health effects. Exposure to DNT can be detrimental to human health, causing harm to the respiratory system, skin, and eyes. Long-term exposure to DNT can cause cancer. And secondly, environmental impact. DNT also causes environmental concerns. It is persistent and can contaminate soil, water, and air, posing risks to ecosystems and potentially entering the food chain. And importance of detection, firstly, for safety. Detecting DNT is crucial for ensuring safety in diverse industries, including explosive manufacturing, waste disposal, and chemical handling. Early detection helps prevent accidents, explosions, and potential harm to workers and the environment. And then monitoring and detecting DNT contamination in soil, water, and air are essential for assessing environmental impact and implementing appropriate remediation measures. In this slide, I will discuss the advantage and disadvantages of metal and graphene plasmonic nanoantennas. Metal plasmonic nanoantennas are structures typically made of noble metals such as gold or silver. They can enhance line matter interactions through the execution of localized surface plasmons, but metal plasmonic nanoantennas experience high energy losses due to intrinsic material properties which limit their efficiency. And then graphene plasmonic nanoantennas utilize the unique properties of graphene, which is a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, like in this figure. Graphene can support surface plasmons and offers low energy due to losses due to its exceptional electronic and optical properties, but graphene plasmonic nanoantennas exhibit relatively weaker light matter interactions compared to metal plasmonic nanoantennas. And there are advantages of metal graphene hybrid plasmonic antennas. Firstly, enhanced performance by combining metal and graphene hybrid nanoantennas can harness the strong plasmonic properties of metals and the low energy losses of graphene, resulting in improved performance. And secondly, tunability. The properties of hybrid nanoantennas can be customized by adjusting the composition and geometry of metal graphene components, enabling tunability in the plasmonic response. And lastly, broadband operation, broadband response, facilitating efficient light absorption, scattering, and localization across a wide range of wavelengths can demonstrate. In summary, metal graphene hybrid plasmonic nanoantennas combine the advantage of metal and graphene plasmonic nanoantennas, thereby overcoming their individual limitations. They provide enhanced performance, tunability, and fine applications in sensing, photovoltaics, photodetectors, and optical communications. And in our antenna design, we utilized the golden ratio. And in this slide, we will definite the golden ratio. The golden ratio approximately calculated as 1.618 is a mathematically ratio. It represents a scenario where the ratio of a smaller segment to a larger segment equals the ratio of the larger segment to the entire length of the line segment. The golden ratio holds great significance in diverse fields such as mathematics, geometry, art, and the natural world. In this study, a hybrid plasmonic perfect absorber has been proposed using a golden ratio-based metal resonators and graphene. The aim of this plasmonic sensor was to achieve the detection of DNT using the SEIRA method. Gold rectangular resonator dimensions LX and LY were chosen by 1597 nanometer and LY 987 nanometer. With following the 17th and 18th Fibonacci sequence numbers, The LX and LY ratio resulted in the golden ratio is equal 1.618. Based on the sensor's spectral response, approximately 95% absorption, as shown in this figure, has been achieved at 5,900 nanometer wavelength. And the rectangular resonator with the golden ratio has resulted in perfect absorption without need for any additional optimization. It is advantage for us. And electrical file and charge distribution, the figure illustrates the electrical file and the charge distribution of plasmonic nanoantenna. As observed in this illustration, structures incorporating graphene demonstrates superior field confinement and higher charge distribution as shown in this figure. By altering the parameters Lx and Ly, new values were obtained at various sizes using the golden ratio. These values have been categorized as GR, golden ratio, GR1, GR2, etc., and are presented in this table. When utilizing these values, a spectral shift towards longer rectangular dimensions was observed. However, there was no significant alteration in the absorption rates, and the resonance mode has shifted towards the right from GR1 to GR5, but this increase has occurred in a linear manner. And in addition to graphene's exceptional file confinement, another advantage is its ability to electrically tune the resonant mode. As depicted in the figure, it is noticeable that as the Fermi energy of graphene increases, the spectral response shifts towards the right. The resonance mode can be electrically adjusted without the need for refabrication. And in this study, the numerical detection DNT was performed using the Seira method with a plasmonic non-antenna structure. In Seira spectroscopy, the vibrational modes of molecules coincide with the resonance frequency of the plasmonic antennas. Therefore, in this method, the absorption dips caused by the vibrational modes of the target molecules are detected in the absorption spectrum of the plasmonic antennas. And DNT gives spectral signatures in 3 different wavelengths, approximately 6,250 nanometer and 6,580 nanometer and 7,500 nanometer. In this figure, the green stripe refers to band 1 of DNT, and the blue stripe refers to band 2 of DNT, and red refers to band 3 of DNT. This demonstrates the influence of graphene on DNT detection. The second derivatives of the signals were calculated, and the amplitudes of the vibrational modes were analyzed. Accordingly, it can be observed that in the sensor with graphene, the amplitudes of the vibrational modes are higher. Figure A represents the structure with only the metal antenna, and figure B represents metal-graphene hybrid metal surface. And lastly, the figure on the side demonstrates the spectral shifts of all vibrational modes of DNT as a function of varying Fermi energy. The Seira effect is clearly depicted at wavelengths of 6,250 nanometer, 6,580 nanometer, and 7,500 nanometer, as shown in this figure. Additionally, by varying the Fermi energy level between 0.1 electron volt and 0.4 electron volt, the spectral shift of the signal has been demonstrated in little picture. And our references, and thank you.
Thank you. Thank you for the presentation. Do you have any questions? If no, so I would like to ask one question about the fabrication errors how it could help to eliminate these errors. Could you please describe some insights?
Which slides? Excuse me.
It is not from the slides. It is from conclusions. That you wrote that the platform, if we implement it practically, it could reduce fabrication errors.
We didn't fabricate this sensor now, but now we are not able a facility, but we will do it soon. And other structures.
Okay. Never mind. Okay, thank you. Thank you for the presentation.
Thank you.
And I would like to invite the last of the session presenter, Saitres Unabi Jeffrey.
Thank you, Professor. Am I audible to you?
Yeah.
Okay, thank you. Okay. Is it clear now? My screen is visible?
Yeah, everything is fine. Please.
Okay, thank you so much, Professor. Good afternoon, everyone. My name is Saitres Unabi, and I would like to present the last presentation of this session. And the title of my presentation is about slum terrain mapping using low-cost 2D laser scanners. And this is a funded project. And I am so much thankful for all the co-authors, whose names are, you can see on this slide. So starting with the presentation. So this is the outline. First, I would like to introduce the topic, and I will show the main component of my research work, which is based on the 2D laser scanners. Then I will present the mechanical and instrumentation design. Later, I will explain the methodology and the real test and their results. So basically, this work is related to the surveying and the mapping of the slum areas or highly populated urban regions. And these areas are actually very rough and narrow that no standard car surveying or other kind of mapping systems can penetrate in these kind of systems. So the main task for us is to design and develop some kind of very slim and low cost motorbike-based surveying mapping system, which can do this specific task. So actually we have utilized some popular 2D laser scanners. So from left to right, there are some common laser scanners available. RP-LiDAR is the most cheapest one. Then we have used the Hokuyu laser scanner, which is in the middle one. And there are some more advanced version of these kind of 2D laser scanners are available, for example, from Czech manufacturers. So technically, this work is based on the electronic electronic data measurement, which we are collecting from 2D laser scanners. And later, I will explain you that we have utilized other sensors to make the 3D pose of the bike and then to make the complete 3D map of the environment. Actually, 2D laser scanners are working. You can imagine this representation that they are detecting the obstacles which are present around to them. So you can see that there is one laser light beam which is rotating, and they are detecting those objects or some walls or any structure which is available in that vicinity which they can sense. So if we are just compiling all these scans from different positions in the surveyed vicinity, for example, here black dots are representing different positions from where we are taking the different scans, so we can compile the complete map of this environment. So using this theoretical knowledge, we have first developed this CAD model of our mechanical system. You can see on the left hand side that we are having one horizontal laser scanner, then we are having one vertical laser scanner, and then we are using stereo camera and some normal cameras available. And there are two units are also available which are invisible here. One is the IMU inertial measurement unit and one GPS. So this is on the right hand side. You can see the actual fabrication of this system, and we have installed this system on the backside of the motorbike. You can see this is the picture before taking some journey to some area. You can see that the person who is having this system, he can now move that motorbike on a very slow speed. now this is the instrumentation design of the system. So as I have informed you that the main parts of our system are 2 laser scanners. So this is the front vertical laser scanner. This is the horizontal 2D laser scanner. And with them, we are having one stereo camera. And additionally, we are having one encoder, which is installed with the wheels of the motorbike. And then we are having one GPS IMU sensor, which is informing us about the acceleration of the bike and the GPS values, latitude, longitude values of the motorbike. Then we have also utilized 3 cameras, front camera, left camera, and right camera to capture the environment where we are moving. This is the picture in which we are explaining the reference frames in which the motorbike is moving. So the blue axis, this blue line are showing the global axis. So when we are starting our journey, we are assuming that this is the X direction and this is the Y direction. And you can see the system which we have installed on the backside of the system is having in the red color, it is the actual vehicle X-axis and vehicle Y-axis. Then we are having XI and Y, which are indicating about the IMU axis, and YL and XL are indicating about the laser scans local references. So what is the actual process is that when the bike is moving, we are first storing all the data using robot operating system. And then we have done the surveying of any vicinity. Then we started to reprocess that data. And first we are doing the pose estimation using the MATLAB software. And then after doing pose estimation, we are performing the 3D point cloud map development. And after that, we are using another kind of software to do the map assessment. So these are the steps which I have explained in the methodology. So first, we are going to find out the 3D pose of the motorbike. So we are having multiple sensors. First, we are having encoder and IMU, which normally we are calling the automatic data. And they are giving us these kind of vector information. These 3 translational changes, and these 3 are the orientation changes which are coming from the encoder and IMU pair. Then the GPS data is informing us about the lat long values, which we are right now converting in terms of meters, and then we are getting this del X and del Y value. Then we are having a 2D SLAM pose we are identifying using the ROS nodes which we are running on the ROS laptop, and those ROS nodes are providing us the X, Y, and theta information from the 2D horizontal laser scanner. And finally, we are having the stereo vision data, and from that stereo vision, we are getting the del X and del Y value of the motorbike system. Now, this information we have actually fused in the Kalman filter methodology. And as you have seen that we are having 2 steps for Kalman filtering. First is the prediction step, which you can see in these 2 equations. So we are actually going to estimate the X vector, which is comprising of the X, Y, and Z, which are the translational data of the motorbike, and the 3 angles of the motorbike. So first we have utilized in the prediction step the encoder IMU data, and then based on the incoming signal, which is maybe either from GPS, from SLAM, or from vision, the correction phase of the Kalman filtering is running. So actually Zn is indicating about the any possible exteroceptive sensor information which can be from these kind of sensors. So after performing the 3D pose of the motorbike, then we are just transforming all the vertical scan data, vertical laser scan data into the global scanning data by using the standard transformation equation. So this is indicating this equation representing the any point belonging to the vertical scanner, and we are just utilizing these translational and rotational matrices to convert that point into the horizontal frame of reference. And then all these horizontal frame of reference point are now going to accumulate in a single vector, which we are calling here STV. And STV is now transforming into the global frame by using the current pose information, which we have accumulated using the 3D point cloud. So we have applied this methodology first in one road, which is available in our campus. And you can see that in that road, we are having very limited features available, and some kind of same scenario we can find on the left-hand side, and some trees having some different views on the right-hand side. So these are the results which we have generated in that particular vicinity. So you can see that the GPS values are having huge errors because of the presence of some trees and some obstruction. So that's why we are having not receiving the correct values. And we are having this sign color is indicating about the autometric values. And you can see that as the journey is going on, these errors are increasing. And now we are having this green color is showing the stereo vision information, and it is also having some errors because if we are not finding the correct matches, correct features from the different images, so we are not getting the correct pose. And the red line, which is hiding in the estimated blue line, is indicating the SLAM result, which is much better in that particular case. And blue line is the resultant value, the final value, which is Kalman filtering is giving us. So after using that blue line, blue pose values, we have converted all the vertical laser scan values. And now you can see in this picture, this is the complete vicinity. This is the complete 3D map of that particular surveyed vicinity. And you can clearly see the left side, there is one wall. Then on the right hand side, you can see different trees have been captured during this process. Now, after doing this step, the last step is some assessment of this map and some value addition if it is required by the user. So there are many softwares available. So we have used the Autodesk Recap, and we have just load that 3D map into this software, and you can see you can do in the runtime different calculation. For example, we have just calculated the total path length, the width of 2 walls, and for example, if you would like to see the height of the trees. So all these things are possible in that particular software. So in this manner, you can see that how much it is now easy to just do once you are surveying, and then you just do on your computer screen all the calculations, and in a very, in my opinion, in a very easy manner. After that, we have done some real tests. So this is the actual slum area. And we have faced a lot of problems to just run our motorbike, and you can see that there are very rough terrain to move that motorbike. So after compiling the 3D pose of the motorbike and the 3D map of the environment, this is the complete representation of the map. And you can see that the height of the objects are very limited because as you have seen in the actual picture, that there are mostly all non-structured environments are available. So that's why you can see there is only one building available, which have some 2 and 3 floors available. And the length of all this terrain was around 90 meters. So after that, you can, again, we can perform the same assessment. So we have just calculated some plantation, some trees, heights, and the total width of the area. And it is applicable to the user if they are trying to find some other thing, for example, the total length. So they can do this thing on the standard softwares. After that, we have selected one very populated region having a lot of small streets. So we have again moved our bike, and then we have reached that 3D map result, which you can see here. And this is again, we have calculated the total length and the total width of this street. You can also calculate some other thing. For example, on the right hand side, we have calculated the stairs area of one house. So this is again very easy to just find out and select any particular region. So after that, we have just compared all these results which we have developed. So our accuracy we have calculated is around 92 to 93%, and you can see that all the results have mentioned here for the slum tent area and for the small street areas. So the conclusion is that the system which we have tested is working very in a good manner compared if we are comparing to other systems, some manual systems, and the accuracy is approximately around 94%. And the more important thing is that the time taken to first do the survey and then to do the assessment is very small, which is not possible with the existing human-based surveying methods. So this is the greater advantage which we are providing with this system. But there are also some deficiencies right now which we are facing. For example, that the stereo vision is always losing some common features, and we are not finding any possible poses from this calculation. So we are still working on this problem, and now we are trying to use the monocular vision information in 3 directions, as I have explained earlier, that we are having front camera, right and left camera, to get the more better Z-axis localization information as compared to the erroneous information from the stereo camera. So many thanks for your patience and listening for this presentation. So I would like to welcome any questions and suggestions from your side.
Okay, thank you. Thank you for the presentation. And do we have any question? Okay, so that the question from my side is about accuracy. You described in the paper that the accuracy is around 94%, yes?
Yes.
What could be the solution to increase? You mentioned about just at the end of the presentation, what kind of solutions could be used, yes? But let's say, what kind of sensors, maybe some sensors could add some value to your increasement of accuracy?
Yes, actually, we have analyzed all the sensors which are providing the data, and this is right now we are finding that the GPS is always having some errors. Then we are using the stereo camera, which is also giving some errors. So that's why we are having now only some limited sensors available. For example, the monocular vision, which is just having a single direction vision information rather than a huge information. So maybe we are having that splitted information applicable for these kind of issues, and then we can solve, we can find some better localization values, especially in the Z-axis.
Okay. Okay, thank you. So thank you, the presenter, for interesting presentation. And I would like to thank you to all the presenters, and would like to close the session. And now we have the technical break until the next session starts.